Alright everyone, welcome to section 3 Star Clusters Evidence of Stellar Evolution. Now, up to this point, we have been looking at how individual stars change over time, how they form, live, and evolve based on their mass. But now we are going to step back and look at group of stars, star clusters, because they give us one of the clearest pieces of evidence that stellar evolution is real. So let's start with this first idea. Star clusters show us stellar evolution happening in real time. Of course, we can't literally watch a single star evolve. It takes millions or billions of years. But if we look at clusters of different ages, we can actually see the changes that happen as the stars grow older. So clusters are like snapshots in a cosmic timeline. So by comparing a young cluster with a middle-aged one and an old one, astronomers can trace out the stages of stellar life just like flipping through a photo album. Now here's a really nice analogy to help picture it. Imagine you are a visitor on Earth who has never seen a tree before. You walk through a forest for an hour and you see all kinds of things: seeds, saplings, big mature trees, fallen logs. So even though you haven't lived long enough to see one tree grow from a seed to a giant oak, but by comparing all those stages, you can figure out the life cycle of trees. And that's exactly what astronomers do with the stars. So we can't live long enough to watch one change, but by observing lots of stars at different ages, especially inside clusters, we can piece together the full story. Now, why are star clusters so powerful as evidence? Because all the stars in a given cluster form together from the same cloud of gas and dust at roughly the same time. And that means they are all about the same age and have the same mechanical makeup. So when we see differences between the stars in a cluster, some still on the main sequence, others becoming giants, we know those differences are not about age or chemistry. They come almost entirely from mass. And that's the key insight. By holding everything else constant, age and composition, clusters let astronomers see clearly how a star's mass determines its entire life story. So star clusters are more than just pretty collection of stars. They are like controlled experiments in nature. Okay, now that we understand why star clusters are so useful, let's see how astronomers actually study them using the HR diagram. Now remember, the HR diagram is one of the most powerful tools in astronomy. It's like a star's report card. It tells us its temperature, brightness, and even its age, all in one graph. So when we plot all the stars in a cluster on an HR diagram with temperature on the x-axis and luminosity on the y-axis, we get a snapshot of that cluster's life story. And every point on the diagram is a star. Hot, bright, young stars sit in the upper left, cooler, dimmer stars lie toward the lower right. And since all stars form together, their distribution on this diagram shows exactly where they are in their evolutionary journey. So it's like pressing pause on the entire cluster, a frozen moment in time that reveals which stars are still burning hydrogen and which have already started to evolve away from the main sequence. Now here's the really clever part, the turn-off point. So what is the turn-off point? The turn-off point is the spot on the HR diagram where stars begin to peel away from the main sequence and move toward the giant region. And that point tells us the age of the cluster. If the turn-off point is up high, where the hottest, most massive stars are, that means those big stars are just now starting to evolve. So the cluster must be young. And if the turnoff is much lower, where only smaller, cooler stars remain, that tells us the cluster is old. So in short, high turnoff means young cluster, low turnoff means older clusters. So these methods gives astronomers a very reliable way to estimate cluster ages without needing to watch the stars change over time. So when we compare chart diagrams for clusters of different ages, the story of stellar evolution becomes crystal clear. So in young clusters, the diagram is still packed with bright blue main sequence stars. They haven't had time to evolve yet. But in middle-aged clusters, the turn-off shifts downward, and you start seeing some stars moving toward the red giant region. And in very old clusters like the globular clusters in our galaxy's halo, most of the stars have already left the main sequence. They have evolved far along their life paths. So by simply lining up these diagrams side by side, we can see what would take billions of years to actually happen. It's like flipping through a time lapse of stellar evolution, all thanks to star clusters. So now we have seen how the chart diagram lets astronomers read the life stories of star clusters. Okay, now that we know how clusters reveal stellar evolution through chart diagrams, let's take a closer look at the different kinds of star clusters we actually observe in our galaxy. Not all clusters are the same. Some are young and scattered, others are ancient and tightly packed. So, understanding their differences helps us see how the environment of a cluster affects the lives of its stars. Now, there are two main types of star clusters: open clusters and globular clusters. So, first let's start with open clusters. These are group of relatively young stars, often just a few hundred million years old, and they tend to be irregular in shape and are mostly found in the disk of the Milky Way, the same region where new stars continue to form. Now a great example is shown here, the Pleiades, sometimes called the Seven Sisters. So you can see it's a loose gathering of bright blue stars surrounded by faint nebulosity. And the blue color tells us the stars are hot and young, still in the early stages of stellar life. Alright, now compare that with the globular clusters. So globular clusters are the elder statements of our galaxy, extremely old, often 11 to 13 billion years in age. And they are very dense and spherical, containing hundreds of thousands of stars tightly packed together. And they live far out in the halo of the Milky Way, orbit in the galactic center. But both open and globular clusters form from collapsing gas clouds, but under very different conditions and at very different times in the galaxy's history. Now, when you look at them side by side, the structural and visual contrasts are striking. So, in open clusters, the stars are spread out, they are far enough apart that close gravitational encounters are rare. And that's why these clusters often have irregular shapes and can look a bit messy. But globular clusters, on the other hand, are tightly packed. So in this image of the Hercules cluster M13, you can see tens of thousands of stars crammed into a nearly perfect sphere. And because of the high density, stars in the core frequently interact gravitationally, and over time they share energy among themselves. So that process smooths out the motion of stars and gives globular clusters their beautiful symmetrical appearance. Now what about how long these clusters last? Open clusters don't stay together forever. Over millions or billions of years, some of their stars move a little faster and eventually drift away. One by one, they escape the cluster's gravity, causing the cluster to gradually disperse. In fact, our sun may have been born in an open cluster that has long since evaporated. And globular clusters, by contrast, are survivors. They are so massive and dense that gravity keeps them bound for over 11 billion years. Even after countless orbits around the galaxy, they remain intact, a living record of the early history of the Milky Way. So, to sum up, open clusters show us the youth of the galaxy, where stars are still being born, while globular clusters are preserve its ancient past. Alright, now let's explore how clusters themselves change over time, from their birth inside collapsing gas clouds to their eventual dispersal into the galaxy. And this also brings up an intriguing question. Could our own sun have once belonged to such a cluster? Let's find out. So, star clusters begin their lives in a giant clouds of gas and dust, the same kind of nebula we have studied before. And as gravity pulls the gas inward, the cloud contracts and fragments into smaller clumps, each one forming a new star or group of stars. Now, sometimes this process produces loose groupings of stars called associations. So, these stars are born together but are too far apart to remain gravitationally bound. And because of that, associations tend to drift apart fairly quickly. The stars simply wander off into space. But in contrast, compact clusters form when the stars are close enough that gravity can hold them together. And these clusters remain stable and can survive for millions or even billions of years. Okay. Now you can think of them as stellar families that stay in touch far longer than their loosely connected cousins. So after cluster forms and stars begin shining, what happens as time goes on? Let's look at how these clusters age. Now over time, even in a stable cluster, stars are constantly moving, orbiting, interacting, and occasionally getting close enough to exchange a bit of energy. And some stars end up moving a little faster than average. So if they reach a speed high enough to overcome the cluster's gravity, they escape into space. And we call this process evaporation, not of gas, but of stars slowly leaking away. Now smaller or more sparse clusters lose stars faster and eventually fade away entirely. And that's why most open clusters survive only for a few 100 million years at most. But the massive globular clusters are a different story. Their immense gravity keeps them intact for cosmic timescales. Many have been orbiting the Milky Way for over 11 billion years, hardly changed since the galaxy's earliest days. And that brings us to a more personal question. What about our star, the Sun? Was it born in one of these clusters? So there's strong evidence that our Sun didn't form alone. It was likely born in a cluster of stars, just like many others in the galaxy. Now astronomers have identified a candidate cluster, M67, which has nearly the same age and chemical composition as the Sun. Now at first glance, M67 seems like it could be our Sun's stellar family. But when scientists trace the motion and orbits of both the Sun and M67 through the Milky Way, the paths don't line up. So while the Sun probably didn't come from M67, its birth cluster has long since dispersed, and its siblings have scattered across the galaxy, invisible to us today. So it's fascinating to think Somewhere out there, among billions of stars, there may still be a few distant siblings of our Sun, born from the same cloud of gas nearly 5 billion years ago. Now, to summarize, clusters are born from collapsing cloud of gas. They evolve and slowly lose members over time. And even stars like our Sun probably began life in such a group. Alright, now with this, we conclude the section 3 of our chapter. So far in section 3, we have seen how star clusters provide us with a snapshot of stellar evolution. And by plotting stars in clusters on the chart diagram, we can read their evolutionary stage and estimate the age of cluster through the turn-off point. Next, we have also learned about the two main types of clusters: open clusters, which are young and sparse, and globular clusters, which are old, dense, and long-lived. And finally, star clusters also give us clues about our own sun's origins. While the Sun likely formed in a cluster, that birth cluster has long since dispersed, scattering its sibling stars across the Milky Way. So in short, clusters let astronomers watch billions of years of stellar evolution in a single glance, making them crucial evidence for our understanding of how stars live and die.